study the decidability, which contains decidable and non-decidable problems. Now we'll go for the accepting. What do you mean by accepting? If T is a Turing machine consisting of set of states, sigma, delta, starting state, and your gamma. T accepts a string W in sigma star if S del W produces S del 1 with star. T accepts a language L in sigma star if for any string W in L T accepts W. Now for this you will have characteristics function for any language L in L is a subset of sigma star. The characteristics function of L is the function psi L of x such that psi L of x is 1 if x belongs to L and psi x L of x is 0 otherwise. For example, if L is a set consisting of W, where W is a string of 0 1 and n1 of W is less than n0 of W less than 2 n1 of W, where n of x W is the number of x present in W. Psi L of W is equal to 1 if n1 W less than n0 W less than 2 n1 of W, and psi L W 0 otherwise. We'll go to definition of deciding. If T is a Turing machine, then T decides a language L in sigma star if T computes the characteristics function of L. T decides a language L in sigma star if for any string W in L T holds on W with output 1. For any string W in L complement T holds on W with output 0. Now accepting or deciding, the example is shown in the figure. The number of states are given, starting state and your halting state H, and in between S and H the states are given P1, P2, P3, P4. A Turing machine accepts the language 0n1, 0n equal to 0 if the input x is in L, T holds with output 1. If the input x is not in L, T hangs. The Turing machine deciding language L is equals to consisting of 0 and 1 and with 0 and 1 and 0 and n greater equal to 0. The P1 hang when input is equals O2 n hang when input, P3 hang when input 0 n m and 0 n, Q1 hang when input 0 n 1 and 0 n plus m, and likewise now a language is recursively enumerable if there is a Turing machine T accepting L. The language is Turing acceptable if there is a Turing machine T accepting L. Example, is given here. 0 n 1 0 n n greater than equal to 0 is a recursive enumerable language. Now, the recursive language L is recursive if there is a Turing machine T residing L. The language L is Turing decidable if there is a Turing machine T residing L. For example, 0 n 1 0 n greater than equal to 0 is a recursive language. I'll go to closure properties of class of recursive languages. Now let's study closure property under complementation. So we'll have a theorem for L be recursive language over sigma, then L complement is also recursive. The proof is given here. Let L be a recursive language over sigma. Then there exists a Turing machine T computing chi L. To construct a tape Turing machine M computing chi L bar or L complement as follows. Starting from T will move to T move right, then we'll have a transition 0, T right 1, transition 1, T right 0. Then L complement is recursive. And the next theorem. So closure property of the union for the recursive languages. If L1 and L2 are recursive languages over sigma, then L1 union L2 is recursive. Proof, we'll have a proof. We will take two languages L1 and L2 which are recursive over sigma. Then there exists Turing machine T1 and T2 computing chi L1 and chi L2 respectively. Now construct a two-tape Turing machine M as follows, as given in the figure. So you copy T1 to tape 2, and T1 turns to T move right, then either way transition 0 to T copy tape 2 to tape 1 will find T2, and with transition 1 we'll have a final state. If the input W is not in L1 and L2, chi L1 W and chi L2 W is 0. Thus both T1, T2 must run and M house with output 0. If the input W is in L1, psi of L1 W is equal to 1, then M house with output 1. If the input W is not L1 but L2, psi of L1 W is 0 and psi of L2 W is 1. Thus M house with output 1. That is M computes characteristics function of psi of L. And L1 and L2 is recursive. Now we'll have the closure property under intersection. Similarly, we'll have proofs. Go to closure property under union. If L1 and L2 recursive number of languages are sigma, then L1 and L2 is also recursively enumerable. Proof is given here. If L1 and L2 recursive enumerable languages are taken over sigma, then there exists Turing machine T1 and T2 accepting L1 and L2 respectively. Now I have to construct an Turing machine as follows. If W is in L1 but not in L2, then T1 in M runs L house. If W is not in L1 but in L2, then T2 in M runs L house. If W is both L1 and L2, then either T1 or T2 runs L house. For these three cases, M house If W is neither in L1 or in L2, then either a T1 or T2 runs, but both never hurt. Then M does not hurt. Thus M accepts L1 in L2, that is L1 union L2 is recursively enumerable. Now we'll study closure property under intersection for recursively enumerable languages over sigma. And I have the proof similar. These were the properties of regular languages. And we'll have for union. We have the relationship between the classes of recursive and non-removable and recursive languages. What is the relation between these classes? Now for first we will have, if L is recursive language, then L is recursively enumerable. The proof that it will be a recursive language over sigma, then there is a Turing machine T deciding L. Then T also accepts L, thus L is recursively enumerable. Let L be a language. If L and L complement are recursively enumerable, then L is recursive. So we are having starting state with T accepts, T complement rejects. If L and L complement be recursive enumerable languages over sigma, then there is a Turing machine T accepting L and T complement accepting L complement. For any string W in sigma star, W is either in L or in L complement, that is either T or T complement must halt on W for any W in sigma star, or any string W in containing the elements of sigma. Now we construct an Turing machine M such that if W is in L, T halts on W, thus M accepts W. If W is not in L, T complement halts on W and thus M rejects W. Then M computes the characteristics function of L, then L is recursive. I'll go to decision problems. A decision problem is a problem whose answer is either yes or no. A yes instance or no instance of a problem P is the instance of P whose answer is yes or no respectively. A decision problem P can be encoded by Fe over sigma as a language. So it's a language Fex, where X is yes instance of P. Encoding of decision problems, if X is a prime, 1 power X, X is a prime. Thus the Turing machine T accepts string ET. If ET is the Turing machine accepting string ET, thus the Turing machine T accepts string W. So these are the cases. We'll go to decidable or solvable problems. First we'll go to definition. If P is the reasonable encoding of a decision problem P over sigma, we say P is decidable or solvable. If this associated language FEXX such that X is a yes instance of P is recursive. A problem P is undecidable or unsolvable if P is not decidable. A self-accepting. So self-accepting is a string or a symbol or string containing 0, 1, hash or any symbol such that W is E of T for some during machine T and W belongs to L of T. Non-self-accepting is a string containing 0, 1, hash or any symbol such that W is equal to E of T for some during machine T and W not belongs to L of T. E encoded Turing machine is equal to W belongs to 0, 1 hash where W is E of T for some Turing machine T. So non-self-accepting NSA is not recursive enumerable. To prove that we assume an SA is recursive enumerable, we prove by contradiction. Then there is a Turing machine T0 such that LT or L of T0 is a non-NSA is E for T0 is in NSA. We have to prove it. If E T0 belongs to NSA, then E T0 does not belong to LT0 by definition of NSA, but LT0 is equal to NSA, thus which is a contradiction. If ET0 does not belong to NSA, then ET0 belongs to SA and ET0 belongs to LT0 by the definition of SA, but LT0 is equal to NSA, thus this is also again a contradiction. Thus our assumption is false, that is NSA is not recursively enumerable. So E is recursive, we have to prove E is recursive. To prove this, you can construct a regular expression for E according to the definition of encoding function as follows. Now we'll have some strings. Then you can say E is regular and thus recursive. SA is recursively enumerable. To prove this, you construct a Turing machine as accepting SA for E. If W is not E of T for some Turing machine T, S rejects W. If W is E of T for some Turing machine T, S accepts E of T if and only if T accepts E of T. The language of S is equal to W such that W is equal to E of T for some Turing machine T accepting E of T is equal to S of A. And S A is recursively enumerable. So S is not recursive. We have to prove NSA is equal to E of SA. NSA is not recursively enumerable from previous theorem and thus not recursive. But E is recursive from the closure property of L1 and L2 are recursive, then L1 minus L2 is recursive. Using its contrapositive, if L1 minus L2 is not recursive, then L1 or L2 are not recursive. Since NSA is not recursive and E is recursive, SA is not recursive. Recursive enumerable. Now I will study the relationship between recursive enumerable, correlations recursive enumerable, and recursive languages. So, if A is a language L, the language L is either recursive or recursively enumerable but not recursive, co-recursive enumerable or but not recursive, neither recursive enumerable or co-recursive enumerable. Then you have the graph Recursive is the intersection part of recursive enumerable and co-recursive enumerable.